Welcome to the class Artificial Neural Networks. This is lecture 1 on deep neural networks, and this is part 1. In part 1, I will present the background and the general objectives of this lecture. We are in a setting of supervised learning for classification. We have p data points. Each data point has an input vector in n dimensions and a target output. If it's a single classification with a single output, then the target is either 1 or 0. 1 means yes. For example, if you want to classify for cars, then yes means yes, this is a car, and the target output would be 1. We use this information to train a network of multiple layers. This is the input layer. This is where the input is applied. For example, the input could be an image or features of an image, and it goes through multiple layers. If it's many layers, it's called a deep network. And then the output is, yes, it's a dog, or no, it's not a dog. Yes, it's a car, if it's a car image. And the aim is to use the information in the training base, in this supervised learning base, to adjust the parameters, to adjust the weights of the network, such that for each image, the network gives the correct output. And importantly, not just for images in the input database, but also for new ones for images in the future. We use our database to train the classifier. We apply an input. The classifier gives its output, which I call y hat. We compare this with the target output that's found in the database or given by a teacher, and we calculate an error based on the difference between those two. Now, the database has many images. This is one car. It's a high dimensional vector, either the pixels or some features extracted from the pixels. And I only show two axes here. And so this is a positive example. I denote this by a green cross. This is another car, another positive example. Then there are non-cars. I denote them by red circles. And then we have many positive examples, many negative examples. So the image looks something like this. The task of supervised learning is to find a separating surface that puts all the positive examples and all future positive examples on one side, and all negative examples and all future negative examples on the other side. Thus, the task of classification corresponds to finding a separating surface in this high-dimensional input space. The separating surface can be defined by a discriminant function, which is positive on one side and negative at the other side, and which goes through 0 at the separating surface. Now, there are particularly simple problems which are linearly separable. Linearly separable means that I can put in a hyperplane that separates the positive examples from the negative ones. A neural network consisting of a single output neuron that's directly connected to the input is called a simple perceptron. A simple perceptron is able to implement a linear separation. That means with a simple perceptron, we can only learn linearly separable problems. I said that in a database, our input has n dimensions. It's a vector with n dimensions. The separating surface, the separating hyperplane, would then have a certain distance to the origin. However, it's convenient to add an extra input and work in input n dimension n+1 and have an extra weight that corresponds to this distance. And then in this n+1 dimensional space, the separating surface always goes through the origin. Learning then means changing the n+1 weights, and that also means rotating the surface, the separating surface in this n+1 dimensional space. Thus, a network consisting of a single layer called a simple perceptron, can only solve linearly separable problems. It imposes a separating hyperplane which in n+1 dimensions always goes through the origin, and we need to adapt the weights. One possibility is to do this by gradient descent, for example in the perceptron algorithm or other gradient descent algorithms. So this is the background. Another question is, well, these simple networks, simple perceptron, can only classify simple problems. What we want is, we want to have training procedures that also work for multi-layer networks. And we'll focus on gradient descent algorithms. Then I would like you to understand why multi-layer networks can solve problems that are not linearly separable, and will construct a solution to the XOR problem. And then of course we consider the backprop algorithm. I will give a derivation and then we also interpret its implementation. So if we have a neural network with many layers, a multi-layer network, the network is more flexible, it's more powerful. And then the question is flexibility always good? And the answer is no, because we have the problem of overfitting and generalization. Because in the end, the network has to work not just on our training database, but also on future data. Let's start with a quick review of gradient descent methods. I said that we use the knowledge in the training base, in the database of supervised learning, to compare the target output with the actual output of the network. This here is a quadratic error function. We take the difference, square it, and then we sum over all patterns. Now we want to minimize this error, and gradient descent does this by saying, well, let's go in the direction of the negative gradient. So here the slope is negative. We go down by increasing the weight. And this is implemented by this formula here. Gamma is a learning rate. Sometimes I call it gamma, sometimes I call it eta. Now we can implement gradient descent in two different versions. We can do it as a batch rule. If we just calculate the gradient, we would have the sum here in the update. And that amounts to saying, I update once I've seen all patterns. And then I update again. With the online rule, I cut out this sum. Every time I've seen a single pattern, I immediately change the weights. Online gradient descent is also called stochastic gradient descent because we may take patterns in arbitrary order. So gradient descent works not just on the quadratic error function, but on arbitrary error function, on arbitrary loss functions. Whenever we want to optimize something, whenever we want to minimize something with respect to the parameters, we can use gradient descent. If we calculate the gradient descent, we will arrive at a batch rule, which means one update after all p patterns. However, often we update after a single pattern, which is the online rule or stochastic gradient descent. And if you have a very, very, very big database, a huge database with millions of patterns, then it might be useful to do something in between the online rule and the batch rule, and that's consider mini batches. We separate our patterns in smaller batches of p over k patterns each, and update after each mini batch. So this is one update step. One epoch is if on average all patterns are applied once. And training is not over after a single epoch. In fact, we have to go down many epochs before we arrive at the minimum. The minimum is not necessarily the global minimum. It could be a local minimum if we have a finite learning rate. And if you're on a local minimum, then at the end we'll also always have a little bit of jitter around the minimum. Good convergence schemes assume that after some time, when you're close to the minimum, you reduced the learning rate gamma. So far for the introduction. Let's have a first quiz. You can pause while watching this page whenever you want to think about the answer. Some of the answers are a bit tricky, but let's start. Your friend claims the following. We can perform gradient descent on all sorts of loss function, not just the quadratic error function. If you agree, raise your hand now. And yes, this is correct. Second claim. If we have p patterns, then p steps of stochastic gradient descent are identical to a single step of batch gradient descent. If you agree, raise your hand now. No, this is wrong. This is wrong for two reasons. The first one is, in stochastic gradient descent, we take patterns in random order. So it's not clear that we, after p patterns, that we have taken each pattern exactly once. The second reason is equally important. Once you have presented the first pattern, you make a change of the weights. So now the network is different. And when you present a second pattern, it already sees a different set of parameters. Third claim. After convergence to a local minimum, a batch gradient descent method with fixed learning rate typically jitters a little bit around the minimum. If you agree, raise your hand now. And yes, this is correct. If you want to keep the jitter small, you have to decrease the learning rate. Final item. After convergence to a global minimum, a stochastic gradient descent method with fixed learning rate always jitters a little bit around the minimum. If you think that this is correct, raise your hand now. And no, this is not correct. Think of the Perceptron algorithm. In a situation where the solution exists, which means the problem is linearly separable, after a finite number of steps, the algorithm has converged. It's a gradient descent algorithm, either in the online stochastic version or in the batch version. Once it has converged, it will no longer change, it will no longer jitter. Thanks a lot for your attention.